Hi everyone, welcome back to the second part of the lecture on coefficient extraction. What we're going to do here is we are going to look at a quotient of two power series, so two generating functions. And we are interested in finding what that is equal to as a generating function. So the idea is we've got some power series, we're going to divide it by another power series, and we're going to write that as a new power series and figure out what the coefficients are. Why is this in the coefficient extraction section? Well, we can look at it from one perspective. What this is really asking is, for this generating function, let's extract the coefficients. And when we extract the coefficients, we've essentially constructed that new generating function C. However, from this perspective, in this video, we are going to look at this as a mechanical process, right back to the definition. So instead of doing coefficient extraction by knowing any specific power series and their coefficients, like the 1 over 1 minus x to the k, and using that, we're going to look at it from a purely mechanical perspective. We're going to say, hey, if I want to write this as a power series, then what that really means is that the numerator is just the denominator times the series that I'm looking for. So I've written a quotient problem as a multiplication problem, or I've written a division problem as a multiplication problem. And that's nice because it says I'm trying to find these values for the C's. I know the values for the A's and the B's. Those are the givens. I need to find the values for the C's. But that, if I look at one at a time, when I multiply these two together, the constant term I get is going to be B naught times C naught, but that's supposed to be A naught. So that gives me an equation that C naught has to satisfy. As long as B naught's not 0, I can divide by B naught and I get an equation for C naught. C naught is A naught over B naught. And so that then tells me, yes, I'm able to solve for that one. And then maybe I can continue on solving for each coefficient in turn. And that's exactly what we do. So there's an initial assumption here. We're assuming B naught is non-zero if A naught is non-zero. If A naught is 0 as well, so both A naught and B naught are 0, then those would be gone. And the numerator and the denominator would each have a factor of x in common, so we could divide out by the common factor of x and then just focus on the resulting series with the x divided out, and this would be our new constant term. And so if A naught and B naught were both 0, we could reduce this and then repeat. So the idea is, as long as A naught's not 0, then we're going to assume that B naught's not 0 so that we could do the division to solve for C naught. If it's not the case, then there's just no solution, so we couldn't do the division. All right, so then how do we get the next term? Well, the next term, we look at multiplying these two and figuring out what the linear term is. So that would be B naught times C1 plus B1 times C naught by the way multiplication works for these power series. The product of B naught and C1 plus B1 and C naught has to be A1. So that gives us this equation. We know everything in that equation except for C1. Again, we know C naught because we just solved it in the line before. So now we can solve this one for C1, and we get an equation involving all known values, A1, B1, C naught, B naught. So we can solve for C1. And so we can get the next term. So we got C naught we've solved for, we can solve for C1, and then we can just keep going. What's the square term? Well, on the right-hand side, it's B naught times C2, B1 times C1, B2 times C naught. Those added together, that's got to equal A2. So that gives us this equation. We know everything in it except for C2, so we solve for C2. And then we can get the next one. So we've got C1, we've just solved for C naught, C1, and now we've just solved for C2. And then we can keep going. And this just shows in general that we can solve for the nth coefficient, and it's in terms of the previous coefficients, Cn minus 1, all the way down to C naught, which we've already solved for, and it also is in terms of the A's and the B's. So in some sense, we can see that this is giving us a recursive method for finding the coefficients of C. We can find C0, and then using that find C1, and using those two find C2, and so on all the way up. So let's do an example. We are going to find the generating function, or find the series expansion for a of x. A of x is this quotient, 1 plus x over 1 minus 2x plus x squared. We would like to write this as a power series. So we want to write it like this. We just need to figure out what the coefficients are. Now, we could use the methods from the first part of this lecture, which just says, go ahead and do coefficient extraction on this. The denominator can factor, go ahead and do coefficient extraction. We'll do that at the end as an alternate approach, because I just want to focus on the mechanical technique that we're developing here. Now, if you are asked a problem to go ahead and find the coefficients for a of x, definitely our methods for coefficient extraction from the first part of the lecture, looking at partial fraction decomposition, those kinds of techniques, doing coefficient extraction using the series we know, 1 over 1 minus x to the k, that's the technique you want to use. However, what I'm doing here is just showing that we can look at this problem of computing the quotient as a purely mechanical problem. We know what division is, we know that it's related to multiplication, we know how to multiply two generating functions. So if we look at it from that perspective, it's a purely mechanical technique to do this. Why am I doing this? Well, one, just to show you the connection with multiplication and to develop this mechanical technique, because sometimes that comes in useful. The other reason I'm doing this is because we're going to see that this immediately tells us that generating functions are connected to recurrence relations. And then that's going to be the whole topic of next lecture. So this is a bit of foreshadowing to next lecture. Okay, so what are we going to do? Well, we are going to say, I want to solve this quotient problem. Well, that's equivalent to solving this multiplication problem. What do I need to multiply 1 minus 2x plus x squared by in order to get 1 plus x? I need to multiply it by something of this form, where I've got to figure out what those values of the a's are. So we'll just go across one coefficient at a time. If I look at the constant term, so the coefficient of x to the 0, what do we have? Well, the constant over here is 1. So I get that 1 is equal to, and what's the constant on the right hand side? It's just the product of these two. So it's a0. And so that tells me that a0 is equal to 1. And there we go. We've just got that a0 is 1. So we've figured out what the first coefficient has to be for a of x. Then we go ahead and look at the linear term. What's the coefficient of x? Well, on the left-hand side, it's 1. On the right-hand side, the coefficient of x is, it's that times that, plus the negative 2 times a0. So it's a1 minus 2a0. We already found out what a0 is. That's 1. So this is a1 minus 2, or in other words, a1 is equal to 3. And so there we go. We found the next one. Again, you can see it's a purely mechanical process. And in fact, it's a recursive process because we're using the previous coefficients to get the next one. So what is the coefficient of x squared? Well, on the left-hand side, it's 0. On the right-hand side, how do we get an x squared? Well, it's going to be a 1 times the a2 minus 2 times the a1, and then 1 times the a0. So it's the product of those three pairs added together. So it's a2 minus 2a1 plus a0. So this becomes a2 minus 2a1. a1 is 3, so that's minus 6 plus a0, which is 1. And so that is a2 minus 5, or in other words, a2 is equal to 5. And so we got the next one. That's 5. And we can continue on. Maybe I'll do the cube term as well. So the coefficient is 0 on the left-hand side. On the right-hand side, it's going to be a3 minus 2a2 plus a1. a3 minus 2a2, so that's minus 10 plus 3, or in other words, a3 minus 7, so that means that a3 is equal to 7. And so we got a3 is equal to 7. And we can keep going. And we can go ahead and find the coefficient of the nth term. Why is that? Why is there a pattern that allows us to find the coefficient of the nth term? Well, look at these last two. What happened there? Well, all that's happening is, in order to get the coefficient of x cubed, let's see what we used. We used the x cubed coefficient, a3, which we're trying to solve, and the two prior, because we're multiplying by this polynomial of degree 2. And the way it worked is we just matched up these two multiply to give us an x cubed term. The linear term had to multiply by the square term to get it as a cube term. And the square term multiplied by the linear term to give us a cube term. And so what happened is a3 was just related to the previous two coefficients. And so on. a4 will be related to the previous two. And a5 will be related to the previous two. And so on down the line. And so what we're getting is that, what is the nth coefficient? Well, there's 0 on the left-hand side. On the right-hand side, it would be an minus 2an minus 1 plus an minus 2. Or in other words, an is equal to 2an minus 1 minus an minus 2. And so we've got a recurrence relation, which is, in this case, second order, which defines the coefficients. And so that's neat, because what it tells us is that we have a way to generate these coefficients recursively. And the way we did it, so ignoring all of the stuff we've done prior with generating functions and knowing these special ones and the way to extract coefficients, we've done it from a purely mechanical perspective. We just said, I want to divide one generating function by another. It's going to have to be something of this form. What do the coefficients have to satisfy? They have to satisfy this equation. So then we work out what that equation is using multiplication, and we're able to figure out the coefficients one after the other as we move down the line. And we get a recursive relationship between those coefficients. So what this shows us is that there is this intimate connection between generating functions and recurrence relations. And this is something we are going to explore a lot more thoroughly in the next lecture. We will actually use generating functions to solve recurrence relations. We'll come up with a technique that in order to solve a recurrence relation, we don't have to do the characteristic polynomial approach and the particular solution and the homogeneous solution and whatnot. We'll come up with an entirely new method for solving recurrence relations, which results in connecting them with generating functions. And it turns out that this connection with generating functions, that's the technique that one implements to write an algorithm to solve a recurrence relation. So if you've ever used something like Wolfram Alpha to solve a recurrence relation, or maybe you've solved recurrence relations in Maple or in Python, there lurking behind the scenes is an algorithm for doing the solution, and it's related, and most likely it's related to the generating function approach, because that gives us a very effective method for solving recurrence relations. So that's what we're going to explore next lecture. For this one, however, what we've done is we've just made the connection now that we can find the quotient by solving a multiplication problem and getting the coefficients one at a time. So if the question was, here's a rational function, tell me what the first 3 or 4, maybe the first 4 coefficients are, we could do it from this approach and just get the first 4 coefficients. Now, in order to contrast this approach, because what we've done now is we haven't actually solved for all the coefficients, but we've got a technique now that will allow us to get the coefficients. We can get any one we want by just going through this process using the recurrence relation. But I want to just contrast this with our alternate solution. We already know how to do coefficient extraction on this thing, a of x. That is 1 plus x over 1 minus x all squared. because I notice the denominator factors as a 1 minus x squared. And what I'm just going to do here is I'm going to use our previous techniques from the earlier part of this lecture, the first half of this lecture, which does coefficient extraction on this thing. If we do that, well, what I'd like to do is I'd like to split this up into the sum of two pieces because each of these pieces are easier to extract coefficients from. And now I want to find the nth coefficient, x to the n of a of x. That's just going to be the nth coefficient of each of these pieces. The nth coefficient of the first piece, well, that's just the generating function for consecutive integers starting at 1. So its nth coefficient is going to be n plus 1. The second piece, the coefficient of x to the n, well, that's the coefficient of x to the n minus 1 in the series with this replaced with a 1, because this just moved everything ahead. Or another way to think about this is multiplying by x to get this rational function. We just multiplied the previous one by x. So all it did was produce a generating function for the series of consecutive integers starting at 0. And so that means that the coefficient of x to the n in that one is just n. And so our coefficient of x to the n in A is 2n plus 1. So we've actually figured out what A sub n is in general using our other techniques. If you think about it, though, there was a lot of information that was used in this line here. It used basically everything we've done up till now in generating functions. We had some specific rational functions that we already knew generating functions for, shifting coefficients, etc. So there's a lot of information that went in here, but this just shows you the power of the amount of content that we've built so far, is that we are able to work out very quickly what the coefficient of x to the n is of this thing is 2n plus 1. And does that work? Yep, because a naught, well, that'd be 2 times 0 plus 1, that's 1. a1, 2 times 1 plus 1, that's 3. 2 times 2 plus 1, that's 5. 2 times 3 plus 1, that's 7. So we actually did get the first 4 correct here using just basic principles. What is a quotient? How is it related to products? What is the definition of a product in this case? And then work them out one at a time. All right, let's have a look at another example. So we want to find a recurrence relation now for the coefficients x over 1 minus x squared using series division. So we're going to go x over 1 minus x squared. That is equal to, it's going to be some c0 plus c1 plus c1x plus c2x squared plus dot dot dot. So in other words, x is equal to 1 minus x squared times c naught plus c1x plus c2x squared plus dot dot dot. If I look at the constant term, what is it? Well, on the left-hand side, it's 0. On the right-hand side, it's c naught. So that gives us c naught is equal to 0. What is our linear term? Our linear term has a coefficient of 1 on the left-hand side. On the right-hand side, it would be c1 minus c0. c0 is 0, so that's just c1. And so that means c1 is equal to 1. Maybe I'll fill these ones in. So that is 0, that is 1, and so on down the line. What about squared? 0 on the left. On the right, it's going to be c2 minus c1 minus c0. And that gives me c2 minus c1, so that's minus 1, minus 0. Or in other words, c2 is equal to 1. We'll do maybe a couple more just to see if we can find a pattern. So what is the next one? Coefficient of x cubed, that's 0. On the other side, it would be c3 minus c2 minus c1. Or in other words, c3, I'll write it this way because it's starting to see a pattern here. This equation, if I just solve for c3, it becomes c3 is equal to c2 plus c1. Oh, and that would then be telling me that c3 is just 2. But it tells me a little bit more than that. It was the sum of the previous 2. And in fact, in general, the coefficient of x to the n, well, on the left it's 0. On the right, it would be cn minus 1 minus Cn minus 2. And I'll fix that first minus so that it's clear. And so this tells me that Cn is equal to Cn minus 1 plus Cn minus 2. That's Fibonacci. So what this tells me is that x over 1 minus x squared is the generating function for the Fibonacci sequence. And if you've ever looked online, Fibonacci sequence, it is more than likely you will see this function hanging around somewhere, Wikipedia or whatever. They'll say, Fibonacci sequence, oh, those are the coefficients of this function. And we've just established that here. We've just established that that rational function does give us the Fibonacci sequence. Okay. What's our next? Oh, we've got an exercise. Find the series for this up to x to the 4. So I'll leave that for you to work on. It's pretty much the same thing we've been doing all along. It's just something that you can practice with. But I will end with one thing related to this previous example. We've done series division. And we did it by looking at it as a multiplication problem. You may be thinking, hey, I've done division before, long division. Does that have any relationship here? And the answer is absolutely. So what were we interested in doing? So I'll just carry on our argument from above here. This is an alternate perspective. So what are we interested in doing? Well, I would like to divide 1 minus x squared into x. That's what I'd like to do. So I'm going to do that. How many times does it go into x? Well, I'm going to focus on that constant part here. How many times does that go into x? Goes in there x times. So then we'll multiply out x minus x squared minus x cubed. Take their difference. That becomes an x squared plus x cubed. And then repeat. How many times does 1 go into x squared? It goes in there x squared times. So then we'll multiply. X squared minus x cubed minus x to the 4th. Take their difference. And we get 2x cubed plus x to the 4th. And repeat. How many times does 1 go into 2x cubed? It goes in there 2x cubed times. So we get a 2x cubed minus 2x to the 4th minus 2x to the 5th. And then we take their difference. And that becomes a 3x to the 4th minus, plus 2x to the 5th. How many times does 1 go into 3x to the 4th? It goes in there 3x to the 4th times. So we get 3x to the 4th minus 3x to the 5th minus 3x to the 6th. Again, take their difference. 5x to the 5 plus 3x to the 6. And we keep going. And what are we noticing? Well, what we are noticing is that the coefficients, 1, 1, 2, 3, and in the next one we'll get a 5. They are the Fibonacci sequence. So if we keep going, we are going to get the generating function for the Fibonacci sequence. So this gives us the Fibonacci generating function. And so that's just an alternate perspective. We did long division here. So maybe I should have indicate that. We will do long division. And we get the same result. So we've done long division here. We got that the quotient is the Fibonacci sequence, or the generating function for the Fibonacci sequence. Back here, we effectively did the same thing. We just didn't do it as long division. We worked out it as a multiplication problem, and again worked out the coefficients one at a time. But basically under the hood, this was the same process. It just looks a little bit different, but we found each coefficient one at a time as we went along. And that's the relationship between these two. They were really the same thing going on, but long division may be something that you're familiar with. You may have done it in previous classes, and it certainly works here as well. All right, so the bottom line for this part of the lecture is that we have worked out now a quotient of two generating functions and figured out what their coefficients are one at a time by just purely mechanical process of working out what the multiplication is and then getting the coefficients one at a time. And in each case, we've related it to recurrence relations. In the next lecture, we will look at this connection between generating functions and recurrence relations a lot more thoroughly. We're going to start with a recurrence relation, and we're going to solve it by producing a generating function where the coefficients are the solution to the recurrence relation, and then we'll try to extract the nth coefficient and thereby solve the recurrence relation. All right, so thanks for watching, and we'll see you in the next lecture.